This video is an overview of the electrochemical cell lab. So in part one, we're just creating a reduction potential table, and we're gonna use zinc as the standard. So you see over here, I have zinc electrodes over here. You actually don't really need to have 5 different pieces of zinc. All you really need is one, and then in between each test, you just clean off this one piece of zinc. Um, so here's how it's gonna go. The red one is the anode, and the black one is the cathode. So in each case, except for magnesium, which is I believe this one here. In each case, this one's magnesium. The zinc is going to be your anode, so you want to connect it to the red one here. And these are just little. These are you'll see in the lab. These are like alligator clips, and the voltmeters they have like this pin right here that looks like that. So it's like a metal thing that you attach the alligator clip to. So these triangles I'm drawing are alligator clips. So you attach it here, and then you attach this one here. This is the copper, so there's the alligator clip, and there needs to be a few drops of copper ion, so Cu2 plus. And in here, it's you use a dropper bottle, and you also put the zinc 2 plus ions here. And you don't need 5 separate pieces of zinc. However, you do need 5 clean wells of zinc ions. So you don't really need these right here, but you do need zinc. You do have to start off with fresh zinc 2 plus ions, because this amount will increase as the zinc gets oxidized in each of these, and it'll actually decrease in this well, because in this one magnesium is easier to oxidize than the zinc, so that's what happens on that one. But on all the other cells that you test, you'll see that the solid the solid zinc electrode is going to get oxidized and turned into zinc 2 plus. So you can't keep using the same well, because this amount is going to increase, and you need to start off, and you want to measure these under standard conditions. So, and we're using 1 molar zinc to do that. Okay, so you do that when you run the test, and then you record your voltage there. Okay, then you unclamp it, or actually you could leave this one clamped. You take it out, so take the zinc out, and then clean it with like sandpaper or steel wool. I'll try to have like sandpaper when we do the lab, and then oh yeah, unclamp this one, of course, unclamp that one, and then you hook it onto the next one. So this is our copper. This is I should have these labeled actually. This is silver. So you have silver ions in this well, and this is like a little piece of solid silver right here. Then you clamp it here, okay, and then take this one out, and then you put it here, put it in the new clean well right here. Then you measure that voltage, and again, that your zinc should be getting oxidized, the solid zinc, and the silver should be getting reduced. We're actually using like cut up pieces of a dime, like I believe it's like 1960. Is it 1963 and before? The dimes were like 90% silver, so that's actually what we're using for the electrode. So don't, and I'll tell you in class, but don't throw those in the waste, because those are actually really pretty hard to find. Because kind of people know about them, the silver, the dimes being 90% silver, and then they like hoard them, and then they're kind of like out of circulation. They're actually really hard to find. So anyway, don't put those in the waste. All right, so moving right along. Again, we don't need a brand new piece of zinc. You can keep using the same one, but you do need a fresh well. So we'll start off with a fresh well, and then we use that same piece of zinc, clean it off, put it in this one. Okay, unclamp the silver, and now the next one. This looks like lead that we're gonna test, or I guess it's a piece of iron. This one's a piece of iron. Okay, and then you'll have a source of iron. Is it 2 plus? I think it's iron 2 plus. Here, I might be mistaken. 3 plus. Well, anyway, then clamp this one. So put the alligator clip there, Okay, and this is actually a little piece of solid iron here. And then you record that data and so on. Then you do the same. So unclamp, clamp on magnesium. This you should have Mg2 plus ions here. Unclamp, clamp. Then unclamp that. Go to just go straight down this line. Okay. And I forgot to mention the salt bridge. So we're gonna dip. So you take tweezers, and then you get a little piece. You're gonna have like strips of filter paper. So one of the group members can actually, it could be one of the first things they do is handle the filter paper. You start cutting it into strips like this, and you take a watch glass with KNO3. I believe it's 1 molar, and then you pour a little bit in there. It's like a giant drop here in your watch glass. You take your tweezers, and then you just dip it through the KNO3, and then you just drape the filter paper strips between, make them probably like an inch, inch and a half. Drape them in between the wells like that. You'll need a brand new salt bridge each time to avoid contamination. So you'll need quite a few of these for this lab. So anyway, you do 5. Everybody is going to be doing these 5 cell reactions, those. And then here you could choose in these wells. You can mix and match. Then you start doing, you could just do 6 other combinations. So I think the procedure says to do a minimum of 6 other ones. So do 6 other combinations here. So for example, you could do like and like magnesium. Okay, you could do that. Oh, one note I forgot to mention about the magnesium. You're gonna have to switch the anode and cathode. So on this one, the red is the anode, which you've been connecting to zinc. So you'll need to, in order to get a positive cell voltage, you'll have to connect this one to this one, and then the cathode actually gets connected to the zinc for that one. So you have to like flip or switch the red and black on that one, or else you'll get the same voltage, but it'll just come out like a negative, and you could just like change the sign. And then you do like 6 other combos here. So if you did copper and magnesium, the copper would be getting reduced by the magnesium. So this would be your cathode, and this would be your anode. The magnesium one, this would be your anode over here. Okay, and then you just do 6 other combos in there. All right, so let's go on to part 2. Let's take a look at this is the data. And yeah, you could see here that when you did magnesium and zinc, that the magnesium ends up being the anode. And we're going to be using these numbers, like for part 3, we're going to be using this number as our E cell standard. So we'll be using that in the Nernst equation. We'll actually be using that value. So we're not using any values from, the standard reduction potential table that we've been using for this whole chapter. We're not using that at all. We're just creating our own in part 1. That's the whole purpose of part 1. Is we're creating like our very own, and instead of hydrogen being the standard, like the standard reduction, so this is what it is on the one we've been using, and then the measured voltage is 0, right? So instead of that being 0, our zinc is actually 0. So we're actually like measuring these all against zinc and seeing how well they get reduced compared to zinc. So anyway, we'll be using this for part 3, the E cell, and we'll be using this one for part 2. So, and the whole purpose of this video is to be an overview. I don't want to really go too much into like the calculations. However, we do need to like think about what calculations we're doing in order to, it helps with explaining like the overview also. So anyway, yeah, this is going to be used for part 2, and this is going to be used for part 3. So let's move on. These are the other ones where you just pick, so this is just sample data. And here these are just the other ones that are not using zinc. So just pick like 6 that you want to do. You don't have to do these. You can just pick any 6 that you want to do. I think there's 7 showing here from this sample data. And again, we'll go over this in the post-lab discussion, but you could see that the iron is actually getting oxidized while the copper is being reduced. So you'll see that the 0.54 was made negative because it's actually the this is showing iron being reduced. So if you look at this reaction, when you do iron with copper, iron's not going to be getting reduced there. It's going to be getting oxidized because the copper is easier to reduce than the iron ions. So that's why this was made negative, because it's now the anode, the iron. So that's why when you see these this data sample, you'll see that some of these are made negative. So again, here likewise the lead is being oxidized. So that's why it was made negative. So when it was reduced compared to the zinc, it was a positive 0.47. But when you compare it, do a cell reaction with copper ions, the lead's going to be getting oxidized. So that's why it's made negative. But again, we'll go over this more in the post lab. So on to part 2. So changing ion concentration. So you'll be making a doing what's called a serial dilution. So you're gonna put 2 drops use a micro, or that's not really a micro pipette, it's just called a pipette, like one of those bulb pipettes, one of those, and then get 2 drops, because the drops need to be equal size. So that's why we're using these and not the dropper bottle. And you put 2 drops of 1 molar copper ions in here, and then so 2 drops go in here, and then you add 18 drops of deionized water. So here's the pipette, and you do 18 drops. And what this gives you is a 1:10 ratio of copper to water, and you're cutting the concentration by you're getting a 1/10 of the original concentration. So in here, when you mix it, so you're going to do 2 drops plus 18 water, and when you mix this up, it's going to be 0.1 molar copper. When you do that, then you take 2 drops of that mixture. You take 2 drops of that, and then you add it to this next one. This is called a serial dilution. So you're going to go 2 drops of the 0.1 molar copper, and then you're going to add 18 drops of water again. So what you're doing is you're getting another 1/10 of that. So it was 0.1. Now this new solution is going to be 0.01 molar after you done adding 18 drops of water. Then you take 2 drops of that and add it here. So you're taking 2 drops of the 0.01 molar copper, and then you're adding 18 drops of water. And you're not doing 1 to 10 just because it's a little easier to measure 2 and 18, because if you did 1 and 10, you would barely have any here to even pick up with the pipette. So it's just easier to measure it. So when you do that, now your new solution is going to be a 1/10 of this. So now it's going to be 0.001 molar copper ions. Then you take that and then you put it in a well right there. Okay, and then you're going to take your 1 molar zinc and your zinc, solid zinc, so you have your solid copper, and then in this well should be 0.001 molar copper ions. Okay, then you connect it here, then you connect this one. So this is your anode, this is your cathode, because it's being reduced there. And then you're going to have a measured value. This is your measured value. And then you're going to also compare this number compared to a predicted value from the Nernst equation. So the Nernst equation is going to go like this. So you'll have E cell non-standard equals E cell standard minus 0.0591 over n times the log of Q. And to get Q, we need to know what the reaction is going to be. So it's going to be zinc getting oxidized. So it'll be 2 plus 2 electrons, and then copper being reduced. So your full balanced equation then is going to be zinc plus copper makes Zn2 plus solid copper. So it's going to be your products over reactants. So Q then is going to be, so Q is going to be the concentration of zinc over the concentration of copper. Okay, and your moles of electrons transferred is 2, because there was 2 electrons here. This is going to be 1 molar, and this is 0.001 molar from the dilution, and this is from part 1. Okay, and if we go back to our data table, our original data table, we're going to use this right here. So we use 0.98 right here. So we use 0.98 volts, or whatever you got. I'm just using sample data, so like whatever you got from part 1 is what you plug in right there. Okay, and then since we know all these values that go into the Nernst equation, we can calculate the predicted E cell, and we're going to compare that to the measured value. Okay, and then we'll comment on like any errors that could have happened. All right, so that's part 2. Now to part 3, we're going to be getting the KSP for silver chloride. So we take our beaker, we're going to do a precipitation reaction. Okay, we're going to add 10 milliliters of 1 molar NaCl. So we're going to add 10 milliliters of it. Okay, that goes here. Then we're going to add, just use the dropper bottle. Actually, I think I have one that shows up. So yeah, use the dropper, add a drop of AgNO3, which is our Ag ions. Okay, and then that's going to mix with the chloride ions. This should be in so much excess that the Ag should run out, and you could assume that it's so much excess that like such a small percentage of it actually reacted. So in our equation, so we're gonna solve for this reaction. So KSP equals anyway, I'll get to that in a second. But so precipitation is gonna happen. You'll get a precipitate here. Okay, then you take one of these pipettes, and then you pick up a little bit, like 1 or 2 milliliters, and then you're gonna put that in a well. So your unknown Ag, because we don't know what this is, it's based on the KSP for the precipitate. So we don't know what the Ag concentration is. We're going to actually solve that. So we don't know what that is. So we're going to grab this with our pipette, and then we're going to put it here. Then you use a little piece of silver, and then you're going to measure it against zinc, the standard zinc one. So you're going to use 1 molar zinc ions here. I had it actually appeared. Okay, and then you measure it. So clamp it here, and then clamp this one, and then you measure it. And then what that's going to do is give you E cell non-standard for this unknown Ag concentration. But we will know this value, okay? And the whole goal here is to calculate KSP. And don't worry, we'll go over this again in the post lab. But the solid Ag is going to be making Ag ions and silver ions, and we don't know what this is. We know what this is. We're going to assume that that this 1 molar didn't change. So this is going to be 1 molar, and the coefficients are 1 to 1. So we plug in 1 molar here, and this we don't know. So if we know what this is, we can solve what KSP is going to be, and that's the whole purpose of the electrochemical cell setup over here, is so that when we plug it into the Nernst equation, I think once I write this out, this makes a lot more sense. So this will be minus 0.0591 over n times the log of Q, and Q in this case is going to be your Ag will be getting reduced, of course, by the zinc, and then it'll be Ag plus zinc 2 plus. So this is going to be 2 right there and 2 right there. So your Q is going to be concentration of zinc over concentration of silver squared. And this is our only unknown. So we know what this is. It's 1 molar. We know what this is. It's 2 electrons are transferred. And this, this right here is from part 1. Okay, so if you go all the way back to part 1, right here. So we're going to use this number for that. So let's go back to 1.41. Goes here. This is 1.41 volts. And we know, and this is from from what you measured right here. So this is from part 3, what you just did. So from the voltmeter, from part 3. So we know this, we know this, we know that's 2, we know this is 1, so this is our only unknown. So you solve for that, okay? And then once you solve for this, then you plug it in right here. It's just times 1, and then that's the KSP. So that's how you do part 3. All right, so I hope this video is helpful for understanding like what's going on and why we're doing what we're doing in the lab. All right, so I'll see you guys when we do the lab.